So in this video, we're going to be covering two more RS configuration problems. Now, if you haven't seen my previous two videos on RS chirality and priority rules, I strongly encourage you guys to watch those videos as well by clicking on the links over here. Okay, so now let's go to our first example for this video. So here we have a triple bond and a double bond, and don't get intimidated by this because we're going to be looking at this in close detail, okay, step by step. So our first step is to first identify all of the chiral centers in this molecule. So let's start on this side over here. Now this carbon atom, it's bonded to 4 substituents. It's bonded to 4 atoms or groups of atoms. However, 3 out of its 4 substituents are equivalent. These 3 hydrogens are the exact same thing. Even though this substituent is different from these ones, since these 3 substituents are the exact same, this center, this atom over here, cannot be chiral. Instead, it is achiral. And this is because a center that's chiral, it should be bonded to 4 different substituents. Each of those substituents must be different from one another. They cannot be equivalent whatsoever, okay? Now let's go to this carbon atom over here. This carbon atom has one substituent over here. It's got a second substituent over here. These 2 substituents are different. However, the remaining 2 substituents of this carbon atom are 2 hydrogen atoms. And these 2 hydrogen atoms, they are equivalent. They are the exact same thing. So since this carbon atom, since 2 of its 4 substituents are equivalent, therefore this atom over here also cannot be chiral. Instead, it is achiral. Now let's look at this carbon atom over here. So here we've got a C double bond, sorry, we've got a C-C triple bond, okay? C-C triple bond. Now, let's look at this carbon atom over here. When you have a triple bond, you can only be bonded to a maximum of 2 substituents. So for this carbon atom over here, it has this substituent and this substituent. Those 2 substituents are quite different from one another. However, again, in order for an atom to be chiral, it's got to be bonded to 4 different substituents, not 2. Therefore, this center is also achiral. You can make a similar case with this carbon atom over here. It's only bonded to 2 substituents, to 2 different substituents, not 4 different ones. Therefore, this carbon atom is also achiral. Let's go to this carbon atom. Now, this carbon atom is bonded to 4 different substituents because this methyl group is different from this CH2OH group, which is different from this group, which is clearly different from this group. This carbon atom is bonded to 4 different substituents, to 4 different things. Therefore, this carbon atom over here, it is a center that's chiral, and we mark it with the asterisk. Now let's go to this carbon atom over here. This carbon atom has a double bond directly attached to it. It can only be bonded to a maximum of 3 substituents, only 3. Because here's one substituent, here's the second substituent, and here's the third substituent, the hydrogen atom. Once again though, in order for a center to be chiral like this atom over here, it's got to be bonded to 4 different substituents, not 3 different ones. Therefore, this center is achiral. When you go to this carbon atom over here, again, it's got a double bond, so it only has 3 substituents. All this hydrogen atom, and this hydrogen atom. And these 2 hydrogen atoms are equivalent. That's another reason why this certainly cannot be a center that's chiral, okay? Because 2 of its substituents are the same, and to top it off, it's only got 3 substituents, not 4. So our only chiral center is going to be this atom over here. So now we have to assign priorities 1 through 4, and let's focus on assigning priorities 1 and 4, and then we can worry about assigning priorities 2 and 3. So in order to assign priorities 1 and 4, the highest and lowest possible priorities respectively, now we have to go 1 atom away. So 1 atom away, carbon, 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 carbon. Well, 1 atom away, you run into a carbon atom. This is where point of first difference really comes in handy, because now we're going to analyze what each of those carbons is bonded to. This carbon has a triple bond to carbon. However, this carbon has 3 single bonds, and these 3 single bonds are all to hydrogen atoms. This carbon over here, it's bonded to 2 hydrogen atoms and to 1 oxygen atom, while this carbon has a double bond to another carbon. So this carbon is bonded to a carbon, this carbon is bonded to a carbon and a hydrogen, this carbon is bonded to 3 hydrogens, and this carbon is bonded to 2 hydrogens and an oxygen. This is where the point of first difference is so important. This carbon is bonded to an oxygen. All these other carbons, they're not bonded to oxygen. They're bonded to either hydrogen and or carbon. Oxygen has a higher atomic number than carbon, and it's also got a higher atomic number than hydrogen. And remember, the higher the atomic number, the higher the priority. Therefore, this substituent has the highest priority of 1. So what about 4? Well, to assign priority 4, let's look at these 3 carbon atoms. This carbon is bonded to another carbon, this carbon is bonded to another carbon and hydrogen, while this carbon is only bonded to 3 hydrogen atoms. It's not bonded to another carbon atom. And since it's only bonded to hydrogen atoms, and since hydrogen atoms have the lowest possible atomic number of 1, this substituent has got to have the lowest possible priority of 4. Because at least these carbons are bonded to another carbon. This carbon over here, it's only bonded to hydrogen atoms. Again, this is where the point of first difference is quite important. So now let's worry about assigning priorities 2 and 3. And this is where it gets a little bit interesting, because you've got carbons here, right? Now this carbon is bonded to another carbon, like I said before, and it's bonded to a hydrogen, while this carbon is only bonded to a carbon via a triple bond. However, when you look at the Cahn-Ingold-Prelog rules, a double bond, you can imagine a double bond as 2 single bonds. Only when you're looking at the Cahn-Ingold-Prelog rules, okay? And you can imagine a triple bond, you can perceive it as 3 single bonds, okay? So therefore, when you have a C triple bond C, okay, it's basically the same as, like, and this is just like the rest of the molecule, that's why I drew these squiggly lines and these lines, okay? We're just focusing on this over here. It's the same thing as this, so C, H3, H3, H3. It's just, so basically this carbon atom has a triple bond to carbon. It's the same thing as this carbon atom having 3 single bonds to carbon, okay? That's how you can imagine it with the Cahn-Ingold-Prelog rules. Now, in reality, this is still a C-C triple bond. However, when you're looking at the priority rules, you can imagine this as being the same as this. So this triple bond, you can perceive it, you can think of it as this carbon having 3 single bonds, and each single bond is to another carbon atom, okay? Now let's look at this double bond over here. When you have a double bond, it's the same thing as this. So you have a carbon atom, and this carbon atom is bonded to 2 carbon atoms via 2 single bonds. That's how you can think of it when you're looking at the priority rules. So triple bond, double bond. So this carbon atom, according to the priority rules, this triple bond is kind of like this carbon atom being bonded to 3 carbon atoms. While this carbon atom over here, based on the priority rules, it's like being bonded to 2 carbon atoms. This carbon atom is therefore bonded to more carbon atoms than this one. And since this carbon atom is bonded to more carbon atoms, this carbon atom wins out based on the point of first difference, and therefore this substituent has a higher priority than this substituent over here, which means that this substituent has priority 2, while this substituent over here has priority of 3. So now we've assigned our 4 priorities, and now we take our right sum, we point it in the direction of the lowest priority substituent, which is going to be the methyl group over here. It's going to be priority 4. So since it's a black wedge, you point your sum out of the page, and now you point your fingers in the direction of 1. Okay, so this is going to be a little complicated, but I have my fingers pointed in the direction of 1. as best as I can, just like this, okay? Next, I curl my fingers. I'm curling, I'm curling, I'm curling, I'm curling, I'm curling. So as I'm curling, I go from 1 to 3 to 2, 1 to 3 to 2, 1 to 3 to 2. Again, we don't worry about priority 4 because priority 4, you only use it when you're determining what direction to point your right thumb in. Do you point it out of the page or do you point it into the page? Once that's done, you only care about 1, 2, and 3 when you're curling your fingers. Okay, so as I curl my fingers, I go from 1, 3, 2, 1, 3, 2, 1, 3, 2. So this is not the natural order of counting. Since this is not the natural order of counting, therefore we have a chiral center that is S. Okay? So now let's go to our second example for this video. Now we're going to find the chiral centers for this molecule. Let's start on this side over here. So this nitrogen atom, it's got a lone pair, and remember, I previously said that if you have a lone pair, it does not count as a substituent unless you're looking at pyramidal inversion. But pyramidal inversion is a significantly different topic, and we're not going to be covering that in this video. So therefore, for the purposes of simplicity and for the purposes of this video and RS chirality, this lone pair will not count as a substituent, and therefore this nitrogen atom does not have 4 different substituents, and therefore it cannot be a center that's chiral. Now let's look at this carbon atom over here. Well, this carbon atom is bonded to your amine group, it's bonded to an NH3, it's bonded to a hydrogen atom, it's bonded to an SH to a thiol group, and it's bonded to all of this. So therefore, this carbon atom, it's bonded to 4 different substituents, it's bonded to 4 different things, which means that this center is chiral. Okay, so now let's go to this carbon atom. It's got a double bond, therefore you cannot have a center that's chiral, and you make the same cases for these carbon atoms. All of these carbon atoms are directly attached to a single bond. Since they're directly attached to a single bond, they can only have a maximum of 3 substituents, like I said previously in this video. And remember, in order for a center to be chiral, it's got to be bonded to 4 different things. Not 3, not 2, it's got to be 4. And therefore, we only have 1 chiral center because this oxygen atom, it can't be a chiral center because it's got lone pairs. Same thing for this thiol group. So we've got only this carbon atom as our chiral center. So now we assign priorities 1 through 4. Hydrogen has the lowest possible atomic number of 1, therefore it's going to have the lowest priority of 4. So now let's go 1 atom away. 1 atom away, we run into nitrogen, we run into sulfur, and we run into carbon. Now, sulfur has an atomic number of 16, while carbon has an atomic number of 6, and nitrogen has an atomic number of 7. If you don't know this, you don't necessarily have to memorize that. You can just look it up on your periodic table, okay? So when you look at your periodic table, like I said in the first video, you have your element here. On the top, you have a number, and on the bottom, you have another number, okay? This is going to be your atomic number. This is going to be your atomic mass, and this is going to be your element. Okay, you don't care about atomic mass, only focus on the number on top. That's your atomic number, that's what matters for a given element. So therefore, sulfur, since it has a higher atomic number than carbon and nitrogen, this substituent is going to have a higher priority than these 2 substituents over here, because the higher the atomic number, the higher the priority. So therefore, our thiol group is going to have the highest possible priority of 1. So now let's look at these 2 substituents. Again, nitrogen has a higher atomic number than carbon, and therefore this substituent is going to have a higher priority than this substituent. So this is going to be priority 2, while this is going to be priority 3. Now we point our right thumb in the direction of priority 4, which is going to be into the page in this case. So pointing it into the page, point your fingers in the direction of 1, just like so, and you curl, you curl, you curl, you curl. As I'm curling my fingers, I go from 1 to 2 to 3, 1, 2, 3, 1, 2, 3. This is the natural order of counting. Therefore, since we do have the normal natural order of counting from 1 to 2 to 3, this chiral center is going to be R. Okay? So those are the 2 examples for this video. If you guys have any questions, comments, or concerns, please do let me know. Thank you so much, guys, for watching.